No.
Yeah, that's pretty straightforward, right?
Okay.
Okay,
Number 8.2.
8.2, yes, good.
Yes.
Now in 8.2, we're going to look at the measures of dispersion. The idea is you see the central tendency, right? You see on average. Okay, I can ask you guys about your, uh, uh, for example, number of siblings in your family. Then you get me right different answers. So I have only one. I have a sister, and you may have more. So we collect this information, and I can first compute the average, right? The mean. So for example, on average, we may have 2 siblings or 3 siblings, right? And then if you look at each individual number, then they are different, right? Someone may have more, someone may have 4 or 5, or someone may have none. So you have an average there, and you also want to know all the values in the data set. How do they, how do they distribute around the average? How far are they around the average, right? Okay, so that idea is called dispersion or spread. Use a plain word, is going to be spread. We're going to see how the data values spread around the mean. So how values spread around the mean. To answer this question, the first thing we can look at is called range. Do you recall what is range? Range is just the maximum value minus the minimum value in a data set. Okay, so again, if we consider this data set here, 11, 19, 22, 35, 35, 41, 52, 52, 68. I just, copy the same data set we used well in 8.1. Then what is the range? You see that the largest, the maximum is 81. The minimum is 11, right? So the range is just 68 minus 11. That gives you 57. What does it tell you? It tells you that, okay, our numbers goes from 11 to 68. And if we look at the difference between the minimum and the maximum, we got 57. So which means all the other values fall, between 11 and 68 over a distance of 57, right? They're all inside here. So if you draw a number line here, you have 11 here and 68 here. And then this, okay, so this distance is 57. And we can see that all the values fall in this interval of length 57. Okay. So this gave us some idea about how those values spread, but the problem is it involves only the maximum and the minimum. It's a very vague picture, right? It's just like you look at you go to a art gallery, you look at a picture from very far away, Okay, once I went to MoMA in New York City, and you know they carried the very famous painting of Vincent van Gogh, the Starry Night. Okay, that was my first time to look at Starry Night like face to face, you know, just within like uh, a few feet. That's very close. And guess what? I was a little disappointed because that painting is very small, actually. That painting is very small. And so if I step back a few yards and then what do I see? I don't see much details, right? I just see a rough idea. So range is just like that. It's just like you look at a painting from a far distance, you only have a very rough idea. So you want to have a better idea about how the values distribute, then you have to look close. You have to involve every single value in the data set. So that comes a better idea of looking at dispersion. It's called standard deviation. Some of you probably took like some elementary statistics either as a separate course or inside another course, and so you've heard of this term. But anyways, let's start from the beginning. Let's start from scratch and see how this term is fabricated. Okay, so let's first consider a data set. 402, 370, 355, 300, 333. A very small data set. There are only 5 values in it. And what can we do first? We can figure out X bar, the mean, right? So let's do it. Maybe you're already trying to compute the mean, see if you can beat me. So see if you get it after I write down all of this. Do you get the whole thing here? What do we get? Okay. If you add all the 5 numbers, do you get 1760? You get 1760? You should. And then the denominator is 5. Again, you divide by 5. No, I don't divide by 5. I first divide by 10, so I get 176, and then multiply by 2. So 352 without calculator. Cool, huh? This can be done without calculator. Okay, then we're going to see, okay, we remember the idea. We want to see how the data values spread about the mean. So the natural idea is, how about let's compute the difference between each data value and the mean. So if I look at each data value, column X, I will have 402, 370, 355, 300, 333. So let's make a table here. Okay, so what I'm going to do is I'm going to look at the difference between each value and the mean. So I'm going to subtract mean from each value. So 402 subtract 352, that is 50. 370 minus 352, that is 18. 355 minus 352, this is 3. 300 minus 352, oh, this is negative 52. And 333 minus 352, that is going to be minus negative 19. Okay, and this is called deviation. Deviation. Okay, so we computed the deviation for each value. We computed deviation for each value. Then what do we see? We see that the idea is the deviation of each value does not give us a good idea of dispersion. It just tells us the distance between each between each value and the bar and the x bar, which is the mean, right? So in statistics, remember, we do not focus on single values. We do not focus on individual values. We always would like to find some trend or tendency in general, which means on average, right? So what we want to know is, on average, how far is each value away from the mean? Okay, so thinking about average here, how do we do average? We take the sum, right? We add every deviation together and then divide by 5, see the average, okay? But then if we go ahead and compute the sum of the deviations, then we're going to add 50 and 18 and 3 and add negative 52 and add negative 19. Tell me the result here. It's pretty easy to see here, right? 50 minus 52, that gives you negative 2. 3 minus 2, that's 1. 1 plus 18 is 19. 19 minus 19 is, 0. Right? 0. So if you want, if you want to see the average, then this implies average of deviations is going to be 0 over 5 is 0. Why? Is this just because our data set is so special that it gave us a sum of deviations to be 0? Not really. Actually, sum of deviations is always 0. It's always 0, right? So what is sum of deviations? How do we get the sum of deviations? See, we add 50, 18, 3, negative 52, and negative 19 together, right? But this is the same as you add all the left-hand side together. So let me copy. Let me copy and paste what we did here. You see that the right-hand side, they add up to 0, which means the left-hand side also add up to 0. Why the left-hand side also add up to 0? Because you see that inside here, if you add all of those, you get the sum of all values, right? And then you look at 352 here. If you add it 5 times, you also get the sum of all the values. So sum of all the values minus the sum of all the values, of course you get 0. So there's no magic here. No matter what data set you look at, you always get 0. Okay, so this means average of deviations is going to be 0. This is not helpful, right? 0 is a nice number, but not helpful for here to for us to figure out the dispersion of data. Okay, so what do we do? Our observation here is why this happen? Because positive and negative deviations, they got canceled out, right? Our observation is positive and negative deviations canceled out. They cancel out each other. Okay, then is there a way that they're not going to be canceled out? So we have a fix here. So our fix is square the deviations. Square the deviations. So I'm sorry, one of the kids is yelling. We go away. Sorry about that. Okay. Okay, so how about let's square the deviations. So the negative number after you square it, it will be positive, right? And positive number after you square it is still going to be positive. And then we add them, we have a positive sum. So in that way, we avoid zero sum, right? So let's back to the table. Back to the table and let's add something to the table. Back to the table here. What we're going to add is, let's add a new column here. So let's square the quantity we get in the second column. So 50 squared is 2,500. 18 squared. Do you recall that somewhere in the lectures before the spring break, when we still have face-to-face meetings, I told you that it is helpful for you to memorize some square numbers. 18 is one of them. That's 324. Of course, we know 3 squared is 9. But I bet nobody knows negative 52 squared. It's the same as 52 squared, and that is 2704. And then negative 19 squared is going to be positive. This is 361. Okay, now what do we see? They are all positive, right? So the sum is going to be positive. Okay, so we call those squared deviations. So let's continue here. Now we have we can compute the sum of squared deviations. So we add all of those squared deviations, we got 5985. So now we're going to take average. Now we take average. So we divide this number by, what's this, the denominator? We want to find the average. So what number do we want to divide? What is the divisor here? Tell me. Are you guys listening? I'm not talking to myself, right?
By 5.
Okay, good suggestion, by 5. By 5 is a good answer. but I'm not going to do it by 5 here. By 5 is a good answer if we are considering the data set as a population. But in this chapter, we consider our data sets as a sample. So as a sample, we're not going to divide by n, we're going to divide by n minus 1, one less than the total number. So I'm going to divide by 4. So divide by n minus 1, since we consider the data set as a sample. Okay, so this involves some some theory behind it, but we're not going to talk about this theory. So we just remember that we are treating all the data set in this chapter as sample. Okay, so when you compute the mean, when you compute the average, it doesn't make any difference. So for sample or for population, there's only one method to compute the mean. But it makes difference if you compute the standard deviation. Okay, and then take the square root. Why we take the square root? Because before we do that, we raise those deviations into squares, right? We square them. If we don't take square root, then we messed up the unit, right? Suppose we're talking about heights of students in my class, right? Then the unit would be, say, inches. Let's use inches, right? And when you find the deviations, you are still subtracting inches from inches, so the unit is still going to be inches. But then we square each of them, then the unit becomes square inches. And after you divide, the unit is still square inches. We're talking about the height of people, so we can't use square inches. So we take square root. So then the unit comes back to inches. So we take square root here. We take square root, we have square root of 5985 divided by 4. And we gave this number a name, call it S for standard deviation. And this is standard deviation of a sample. Okay, and plug this into your simple calculator. This is about, if I keep 2 decimal places, 38.40. Okay, so this is called the standard deviation. So this is called the standard deviation, actually, of a sample. Okay. And which is used to measure the dispersion of data. In the next section, you will see how we are going to use the mean and standard deviation. I believe most of you heard of the bell curve or the normal distribution, right? So we're going to see that in the next section, but today we're just going to learn how to compute standard deviation for a sample. Okay, so let's write out a little summary here. Steps of finding this s here. So what do we do at the very beginning? We find the sample mean, right? Which we call it x bar. We find the average first, and then we find the deviation for each x. So we call it x minus x bar. That's the second column in the table, right? And then we square each deviation. And next step, we find the sum of all deviations. We find the sum of all deviations. And now we are at the point that we can find the standard deviation, which is given by the square root of, if I write it in words, the numerator is sum of squared deviations. Sorry, I missed a word here. Squared. Find the sum of all squared deviations. So sum of squared deviations, it goes here under the radical in the numerator. And what is denominator? N minus 1. Okay. And so if I want to use symbol to write this, in the numerator I have the sum of all the deviations squared, and the denominator is N minus 1. So here N is the number of values in the data set. Number of values in the data set or in the set, the same thing. Okay. Okay. So how about let's do another example and see if we can follow those steps. So the exercise here is find the standard deviation of this data set 8, 6, 9, 1. You know, normally we do not compute standard deviation by hand, because data set usually is pretty big, and we use computer to find the standard deviation. But to understand what is standard deviation, it still makes sense to compute by hand on some very small data set. Just show us the understanding of that. Okay, sorry about that. I have to, keep another kid away from me. Okay, so let's do this. Let's first find X bar here. Find the mean. So we add all the 4 numbers together and divide by 4. This is pretty quick, right? So numerator is 24, divide by 4, mean is 6. Then we set up the table. So we see the values here, column X. How many values of X? 8, 6, 9, 1. Right? And in the second column, we compute X minus X bar. So 8 minus 6 is 2. 6 minus 6 is 0. 9 minus 6 is 3. 1 minus 6 is -5. In the next column, we're going to square the difference. So 2 squared, I get 4. 0 squared is still 0. 3 squared is 9. Negative 5 squared. Now you know this is not negative 25, which is 25. Okay, so we have all the squared deviations. What is the sum? The sum here is 4 plus 0 plus 9 plus 25, which is 38. So now what is our standard deviation as? It's going to be square root of 38 divided by how many data values do we have there? 4, right? But we don't divide by 4 since this is a sample. We subtract 1, so divide by 3. So this is square root of 38 divided by 3. And well, I could have taught you how to find square root by using by hand, but nobody's doing that nowadays. Just use a simple calculator or Google. This is 3.56. So this is the standard deviation. Okay. Now we know how to compute mean and standard deviation. So we have good preparation for the next section for the bell curve. And we'll see some nice application there. But before I let you go, I want to give you another exercise here. So I have this data set, 5, 5, 5, how many? 4, 5, 6. Okay, there are 6 values and they're all 5 in this data set. So let me ask you 2 questions. What is the mean? What is the mean of the data set? Do you have to compute? In this data set, every value is 5. Do you have to compute the mean? Do you have to add all the 5s and divide by 6? Tell me, are you going to do that? Dylan, are you going to do that?
Well, yeah, because.
Or do you have a quick answer?
I feel like you have a quick answer.
Okay, Arlington, what is the quick answer?
Would it be 5?
Yeah, it's 5, right? Everyone is 5.
Okay.
Everyone is 5. Everyone is the same. So the average is still the same, 5. No computation is needed. And what is the standard deviation? What is the standard deviation?
5. Wouldn't be 5. No.
What's the standard deviation?
It'd be 0, wouldn't it?
Yes, why 0?
Because you're doing 5 subtract 5 and it equals 0 for all of them, right?
Okay, yeah. If you compute the deviation, you got all zeros. So
Yeah.
the square is still going to be zeros. But you even don't have to go that far. Why 0? Because the data values are all the same. So there's no dispersion, right? The data values are all the same. So the mean is going to be the same. And all the data values are the same as the mean. There's no dispersion, which means standard deviation is 0. Okay, as is 0 because there's no dispersion. Okay, no